Bridging Mathematics, Solid Mensuration, Surface Area, and Volume of Solids. So again, for this video, I'm Engineer Brian J. Guzman, and I will be your instructor or lecturer. So this time, we're just going to introduce various solids and identify the different formulas for the computation of surface areas and volumes of solid. So we mentioned on the last unit that solid mensuration deals with the computations of areas of plane figures and volumes of solids. Okay, so we're already done with plane figures, so now we're going to discuss solid. So what is a solid? So a solid is any limited portion of space bounded by surfaces. Okay, so remember, plane figures are just what? Let's say two-dimensional or flat. Therefore, they can only contain perimeters, measures of lengths, and areas. Okay, this time solids are now limited or bounded in space, meaning they must now contain particular volume. Okay, so solid, three-dimensional, plane figures, two-dimensional. So a section of a solid is the plane figure cut from the solid by passing through it. So if you pass a plane, okay, through a solid, you're going to create a plane figure, which were our last topic, or which were the topic from our last unit. Thus, in the case of the solid shown, let's say here, plane M, okay, the plane M here, cuts from the solid the section A, B, C, D, E. So that's how you relate now, okay, solids. So if we're going to relate this with your discussion in analytic geometry, okay, so the reason why they are called conic sections is because the parabolas, the ellipse, and the hyperbolas were all cut, or were all planes passed in a cone. Okay, so that's a very good relationship between the two. The reason why they're called conic sections is because those figures or those shapes are passed from a cone. That's how you form parabola, ellipse, and hyperbolas. Okay, so here, let's say polyhedrons, or this one's, a polyhedron is a solid bounded by planes. The edges of a polyhedron are the intersections of the bounding plane. So these are examples of polyhedrons. The faces are the portions of the bounding planes included by the edges. The faces are polygons. Okay, the vertices are the intersections of the edges. Okay, so if for plane figures for two-dimensional, you have your polygons. Here on three-dimensionals, you have your polyhedrons. Okay, there are different types of solids. Some textbooks or some references tend to define them with respect to the formula of the computation of their volumes. Okay, so some textbooks will divide these types of problems or these solids when it comes to volume. Let's say volumes wherein the volume is equal to base times height. The solids wherein the volume is equal to 1/3 base height. Okay, the solids wherein the volume is equal to mean base times height. Okay, and so on and so forth. But for simplicity purposes, I've chosen to divide them by prisms. Let's say prisms, cylinders, cones, and spheres. Okay, and pyramids. Okay, so let's try to define them by that. So let's start with prisms. So a prism is a polyhedron whose bases are equal polygons in parallel planes and whose sides are parallelograms. Prisms are classified according to their bases. Thus, a hexagonal prism, so this one is a hexagonal prism, is one whose base is a hexagon. And a regular hexagonal prism has a base of a regular hexagon. Okay, so take note, a prism has, okay, whose bases are equal polygons in parallel planes, whose sides are parallelograms, so equal polygons. So if say here, it's as if you have a hexagon and you pulled it so that it will gain a height or a thickness. On the opposite side, okay, of this figure is also another hexagon. Prisms are defined by their bases. The base of this prism is a hexagon, therefore it's called a hexagonal prism. Okay, so if this was a rectangle, it's called a rectangular prism or a rectangular parallelepiped. But we'll get through that later. Okay, the most common thing about prisms is that majority of them, especially those regular prisms, okay, have a volume, or the formula for their volume is equal now to the area of the base. So whatever the base is, if the area is a hexagon, that's the area of the hexagon. If a base is a square, that's the area of a square multiplied by the height or the thickness attained by the prism. Okay, so this is the formula for prisms. So the axis of a prism is the line joining the centroids of the bases. So here you have a line, okay, joining the centroid of this hexagon to another hexagon there. A right prism is one whose axis is perpendicular to the base. So if this height is perpendicular to the base, to the hexagonal base, meaning it's a right prism. The height h of a prism is the distance between the bases. Okay, so the distance between the bases is now the height. Take note, this is a vertical or a perpendicular distance. Okay, so a good example of a prism is your rectangular parallelepiped. So a rectangular parallelepiped. Okay, so this is an example of a prism because it's a, let's say, a square or a rectangle, okay, as a base, or it has a square or rectangle as a base. So in these succeeding examples, I'm just going to give you a figure and then the corresponding formulas for their most of the time their volume, or most importantly their volume, their total surface areas, and then other relevant formulas. Okay, so for a rectangular parallelepiped, this is the volume. The volume is straight from the volume of a prism, the area of the base, okay, times the height. Now you might be wondering, sir, what is the base? So if we recall back, okay, in our discussion for plane figures, the base is usually the one that is now horizontal or flat on the ground. Okay, but again, that is interchangeable depending on the orientation this time of the solid. Okay, so in this rectangular parallelepiped, our base is A times B, the rectangular base here, and our height is C. Okay, therefore AB, that's the base, times C. But if you rotate this, if you stand it vertically, correct, the base is B and C, that's the area of the base, okay, times the height of A. But you'll get BC times A, that's the same as ABC. Okay, so you'll get the same volume anyways. Okay, so the total surface area, so this is a very good one. Okay, this the total surface area is now the areas of all of the polygons that is now covering your solid, or that is now enclosing that specific volume. So think of it this way. So if the surface area is like the wrapping or the gift wrapping paper, if you might say, that will wrap around your solid. Okay, so since this is a total surface area, it must cover all of the surfaces. So in this rectangular parallelepiped, how many surfaces do we have? So we have 1, 2, 3 here below, then 4 on the other side, and then 5, this one, and then 6 on the other side. Okay, so if we're considering the total surface area, you add all of those areas together. So AB, 2, 1, 2, BC, 2, 1, 2, and then AC, 1, this one, and then 2 at the back. Okay, so twice. But if you're considering only the lateral area, okay, the lateral area, this is most of the time the area that is just covering the sides. Okay, so not the top and the bottom part. Again, so the lateral area is only the one covering the sides, okay, of your solid. Of course, depending also in the orientation. Okay, but most of the time that is just the sides of the solid. So you see here in this particular figure, correct? So what are the plane or the areas covering the side only? AC, 2 of them, correct? And then BC. Did not include A, B, the top and the bottom part. That's your lateral area. Okay, so again, volume, lateral area, and total surface area. Volume and surface area are your main quantities here. Lateral areas, okay, and the among other formula or the other formulas are just miscellaneous or necessary when the problem demands it. Okay, so I'm going to focus on these two, volume and surface area. That's for a rectangular parallelepiped. Next you have your cube, of course, a regular hexahedron. So for a cube, just simply multiply 3 times or the edges to itself by 3. Okay, this is also a rectangular parallelepiped. It's just this time all of the sides are equal. Okay, so these are the formulas for the volume and the surface area. Okay, that's for a cube. Okay, let's go to pyramids. So pyramids, as you all know, usually when you think about pyramids, the main shape or the main basic shape that comes into your mind might be triangles, and you are correct. Okay, because a pyramid is a polyhedron with a polygonal base and triangular faces that meet at a common point called the vertex here. Similar to prisms, pyramids are classified according to the bases. Okay, so what type of pyramid is this? How many sides does the base have? 1, 2, 3, 4, 5. So it's a pentagon. Okay. So the pyramid usually is given by the formula, or the volume of the pyramid is usually given by the formula 1/3 times the area of the base, so whatever shape this is, the area of the pentagon, multiplied by the perpendicular height again. Okay, so you must keep it in your mind now that h is always the altitude, and altitude is always perpendicular to where it is based from. Okay, so base is a perpendicular height. So how do you compute for the volume of a pyramid? Solve for the area of the base, whatever shape that is, and then multiply it by its altitude and then divide it by 3. Okay, that's for a pyramid. A frustum of a pyramid. Okay, a frustum of a pyramid is the volume included between the base and a cutting plane parallel to the base. Now a frustum is this one. Okay, so without the cut, so without removing a part here, this entire figure is a pyramid, correct? The solid is a pyramid. But if you remove, if you pass a section somewhere in between the base and the vertex and then cut, okay, the remaining solid above, you form now a frustum. So this is usually common in pedestals, correct? Wherein now you're going to form this particular figure. This is also very common in earthworks. So sometimes frustums are present. Okay. So for the area of the frustum, for the volume of the frustum, so this is the formula. Okay. So A1 is the lower basis area, A2 is the upper basis area, and H is your altitude. Please, this is a very important formula. Follow this one, or you recall to this presentation when you encounter a frustum of a pyramid. There are other types of frustum that we'll discuss later. Okay. Cylinders. Okay, so cylinders, the main shape might be going to your mind is probably a circular or an elliptical or a curved shape. Okay, and you are correct. Okay, so a cylinder is the surface generated by a straight line intersecting and moving along a closed curve. The directrix, this one, while remaining parallel to a fixed straight line, it is not on or parallel to the plane of the directrix. Like prisms, cylinders are classified according to their bases. Okay, so cylinders are now a bit more fluid. Fluid is a very confusing term. Let's say curved type of prisms. Okay, so if prisms are composed of polygons, or the bases of prisms are polygons, for cylinders their bases are usually curved, like a circle, like an ellipse. Okay, so you have of course your right circular cylinders, wherein the base of the cylinder is, okay, a circle. So the volume of cylinders is also very similar to the volume of prisms. So the area of the base also multiplied by the height. But this time your bases are not polygons, but they are sometimes circular and elliptical. Okay, so its lateral area is of course this one, the base perimeter times height. That's your cylinder. Where do you usually cylinders? You see cylinders, water tanks, right? Canned goods, correct? That's where you see cylinders. Okay. Cone. So again, so if cylinders is to prisms, cone is to pyramids. Okay, so cone, the usual shape that comes into your mind, is also circular but with a tip, correct, or with a vertex. So cylinders is to prisms, cone is to pyramids. A cone is the surface generated by a straight line, the generator passing through a fixed point, the vertex, and moving along a fixed curve, the directrix. Similar to pyramids, cones are classified according to their bases. Also, the volume of cones is usually given by this formula, 1/3 of the base, area of the base times height. Similar to cylinders, this time, the bases are usually curved, circular or elliptical, or even other types of curved shapes. Okay, so right circular cone, this one, a circular cone. Okay, so the volume of this one is 1/3 the base times the height as well. Since the base is a circle, that's 1/3 pi r squared times height. Okay, L is a slant height, meaning it's not a perpendicular height, but it's the slant height of your cone. This was derived from the Pythagorean theorem. The lateral area is given by pi r times the slant height. Okay, so these formula are very easy to use. Remember, since there are a lot of them, not quite, but since you have used this presentation, this can serve as your reference already. Okay. Frustum of a cone. So if a pyramid has a frustum, so does the cone. So if you again pass a cutting plane between the base and the vertex of a cone, you're going to form a frustum. And the volume, the formula for the volume, is the same of that of a cylinder. But of course, what will change is now the computation for the area of the bases, correct? Because for cylinders, they are polygons. Here they are circular or curved shapes. And last but not the least, you have your sphere. Your sphere, okay, is from your circle, okay, or somewhat related to your circle in plane figures. So this is your sphere, correct? A usual notation or usual example for a sphere is, of course, a ball. Okay, so for a sphere, the volume is given by 4/3 pi r cubed. If you are now having a diameter of the diameter of the sphere is given, simply divide that diameter into or by 2. The surface area is 4 pi r squared. So this is a very common board exam problem, spheres. Okay, so kindly memorize this one. Spherical segment. So we had what they call this segment of a circle, correct? So we also have spherical segment of one base. So this is a spherical segment of one base. Okay, so for the segment of a circle or for the sector of a circle, we had that something you call your arc length, correct? Here in solids, we have something you call your zone. So the zone is the piece of surface that is now covering your spherical segment. Okay, so the area of a zone is equal to 2 pi r h, h being the height of the zone itself, r being the radius of your circle. The volume of a spherical segment of one base, take note, okay, is pi h squared over 3 multiplied by 3r minus h. Again, these are formulas, okay, so kindly, this will be as your reference, okay. If you have spherical segment of one base, you can also have spherical segment of two bases. So this is somewhat like a frustum, okay, for a spherical segment. So if you have two bases, okay, the formula for the area of the zone stays the same. So 2 pi, the area of the zone, let's say 2 pi r h. So this is zone, okay, or the surface around it, okay, 2 pi r h. But the volume changes. A being the radius of one base, B being the radius of the other base. Okay, and that's it for your spheres. Again, wait, you still have spherical cone or spherical sector. So this was the pizza or the the sector of a circle, correct? So this time, if you go to solids, if you convert into a solid, this becomes now a spherical cone or a spherical sector. So it looks like somewhat like a snow cone or an ice cream cone, correct? So the area, the volume is 1/3 area of zone times the radius. What's the area of zone a while ago? So we had that in the formula for spherical segment, correct? Multiplied by the radius. That's how you solve for the spherical sector. Okay? So we can now proceed with your examples. Example number 1. A masonry dam 40 feet high has a uniform vertical cross-section as shown in the figure. The dam is 80 feet long and its material weighs 125 pounds per cubic foot. Find the weight of the dam. So this is a very common problem in fluid mechanics when you are now analyzing dams, okay, or dam analysis. Okay, the very common or the very first thing that's going to be asked of you there is to compute the weight of the dam itself. Okay, so this dam is having a particular cross section. So if you look at the side of the dam, okay, this is what you're going to see. And then according to the problem, this dam is 80 feet long. So if you imagine that, so the 80 feet is actually, okay, 80 feet perpendicular to your screen, or so wherever you're viewing this. Okay, so the 80 feet distance is now, let's say, protruding from your phone screen or from your monitor screen. Okay, that's how you know. So this is just a cross section of the dam, but it's the same all throughout. Okay, so this is your dam itself. The question is, what is the weight of this dam if it has this cross section and if it weighs 125 pounds per cubic foot? Okay, so here, since the masonry weighs 125 pounds per cubic foot, the weight of the dam is what? Okay, so if you have something, let's say 125 pounds per cubic foot, if you have 1 cubic foot, of course you have 125 pounds. If you have 2 cubic feet, you have 125 times 2, that is 250 pounds, correct? Same in your, let's say, market. If tomato is worth 125 per kilo, that's a very expensive tomato, correct? Let's say chicken, kano ba bentahan yun? Hindi ko alam. Basta, okay, what costs 125 pesos per kilo? Natang di na mamalengke. Let's say chicken neck. Chicken neck. Okay, so if chicken neck costs 125 pounds per kilo, 125 pesos per kilo, correct? If you buy 1 kilo, okay, so that gives you what? 125 pesos to pay. If you buy 2 kilos, okay, that gives you 250 pesos to pay. So same here. If your dam weighs 125 pounds per cubic feet, correct? How do you determine the weight? Well, you need to determine how much feet or cubic feet is present in your dam. Therefore, we say for the total weight, we multiply the weight per cubic feet, 125 pounds per cubic feet, by the volume of the dam, correct? So we must identify first the volume of the dam before we solve for its weight. So the dam is in the form of a prism of altitude 80 feet with trapezoidal bases. So imagine this now as a flat, okay, figure, and then its height is 80. Okay, that's your figure. So the volume of the dam is the volume of a prism. Remember, the volume of a prism is given by, okay, the area of the base, okay. So here, the volume of a prism is the area of the base. We take that equal to B, okay. So the area of the base B is same as A sub B, okay, times the height. What is our height? Our height is 80 because that is 80 feet perpendicular to your screen, correct? So the area of the base B of the prism is computed using the area of a trapezoid that we've learned or we've discussed or introduced in the plane figures. Okay, so the B or A sub B is now the area of the trapezoid, which is 1/2 the sum of the bases, the parallel bases multiplied by the height. Take note, this H here is a different H from the H of the prism. Okay, so H of the prism is used for volume, H of the trapezoid is used for the area of the trapezoid. It just so happens that they have the same variable. Okay, so you just need to differentiate them. Okay, so the base of the trapezoid, so where are the, so recall a trapezoid has one pair of opposite sides parallel. Where are the opposite sides that are parallel? That is your 4 and your 16. Okay, 40 is a vertical side, but this side is not vertical, therefore they are not parallel to each other. So the parallel sides are 16 and 4. What is their altitude? That is your 40. Because this is a vertical side, these are horizontal, therefore they are perpendicular to each other. Okay, so base 1 is 16, base 2 is 4. That gives you 16 and 4. H is 40, so the base or the area of the trapezoid is, okay, this one, 400 square feet. Therefore, the volume of the dam is, so we go back here, we use this area of the base, A sub B equal to 400 square feet here. So take note, now we're going to use H as the volume or as the altitude of the prism. This is no longer the trapezoid because we're already done using the trapezoid. We already got the area, correct? So simply multiply the area of the base, 400 square feet, to the height of the trapezoid, perpendicular to your screen right now. Okay, that is now 400 square feet times 80 feet. Square feet times feet gives you cubic feet. So we have now a volume. So it turns out the volume of the dam, so it's worth, or it has now 32,000 cubic feet of masonry. How much will this dam weigh? So if you have 125 pounds per cubic foot, and you have 32,000 cubic feet, simply multiply the two, cancel out the feet, it will give you pounds. So the dam weighs 4 million pounds. Okay, so the dam weighs 4 million pounds. It makes sense. That's a dam, and that's masonry. That's very, very heavy. Okay, so that is your answer for example number 1. This one is an example of a prism. Okay, example number 2. For example number 2, this is no longer a prism, but turns out, or it seems that this one is a cone. Okay, so the upper portion of a Sorbet glass is in the form of a right circular cone with a base of radius 2 inches and a slant height of 4 inches. Inner dimensions, okay? So that's relevant because we consider the glass as having a specific thickness, okay? But we disregard the thickness of the glass itself. First, find the volume of liquid it contains when full. That's the first one. And B, when filled to a depth of 3 inches, okay? So we ask only for the volume of liquid it contains at full capacity and when that liquid is only 3 inches high. Okay, so solution number 1 for the volume when full. Since this is a cone, okay, so recall for a cone that is 1/3 area of the base times height. The base of our cone is a circle. What is the radius, okay, of the base? That is 2 inches, okay? Take note, we are considering full capacity here. So we're going to fill this up, okay? So the vertex of this cone is B, okay? The center of the circle's base is O. And then the edges of the circle are the quadrants of the circle are A and C, okay? So 1/3 area of the base times height. So again, B is equal to area sub A sub B. Some textbooks or some references uses, okay, B as the area of the base, okay? So the B is equal to the area of the circle. Since this is full, this is not our water level, okay, or liquid level. The liquid level is here at AC, at level of A and C, correct? Therefore, the radius of that liquid is now 2 inches, okay? So the radius of that liquid, the circle, okay, is now pi r squared, circle of course, pi times 2 inches squared. So the area of the base of the cylinder, full, okay, is now 4 pi square inches. What about the height, okay? So the height of the circle is what? So if you're considering full, therefore the water, the liquid level is here at O, okay? So the height of the circle is now B to O, or O to B, okay? 3 inches here is the height of the liquid for question B, when a depth of 3 inches. So disregard this for now, okay? So the height of the liquid is OB. How do we solve that height? Well, notice that you have a triangle here, triangle AOB, correct? So using triangle AOB and the Pythagorean theorem, okay, what do we get? How can we use the Pythagorean theorem? What sides of the triangle do we have? Well, we are looking for the altitude, that is now side BO or OB, correct? The other leg is 2 inches and the hypotenuse of the triangle is now AB, correct? So Pythagorean theorem, hypotenuse. So if you remember our discussion in trigonometry, that is the square root of hypotenuse squared minus the leg squared. So 4 squared minus 2 squared gives you OB, which is now 2 square root of 3 inches. You can convert this into decimal, but I suggest using this value for minimizing for accuracy, okay? So now that we have the area of the base, now that we have the height, OB, total height, we can now solve for the volume at full capacity, which is simply 1/3 4 pi square inches times 2 square root of 3 inches, which gives you 14.510 cubic inch, okay? So for final answers, it's best to describe them in their decimal form, okay? So this is at full capacity, but what if you do not fill it up until the brim, okay? So that's your letter B. So for the volume, when the liquid depth is only 3 inches, okay? Of course, that this volume must be significantly lower than the volume at full capacity, okay? However, we are still using a cone, correct? A cone of smaller volume, okay? So how do we do that? Well, what changed in our problem? Well, the slant height is no longer 4, correct? The radius is no longer 2, but we now have the altitude of our cone. The altitude is now given as 3 inches, no longer OB, okay? So here, we have an altitude of already 3 inches. So we're no longer going to solve for this one. The problem here is, okay, to solve for the area of the base of the cone, that is now using the radius r, which is no longer 2. Of course, this value must be smaller than 2, correct? So how do we now solve for the value of r? Well, if you consider two similar triangles, let's say that larger triangle for the glass is full, for when the Cherbe glass is full, that is triangle AOB, with a radius or with the radius of 2, it's 2, with the height of OB, 2 square root of 3, correct? And with the hypotenuse of 4, okay? If you draw this triangle, cross-section of the cone, correct? You can also draw another smaller triangle, which is now the liquid depth at 3. The radius of r, and then the height of 3, and then a smaller slant height or hypotenuse, okay? These two are similar figures, therefore ratio and proportion can be used, correct? So by ratio and proportion, we say r is to 3 is equal now to 2 is to 2 square root of 3. So solving for r, we get 3 over square root of 3 inches, okay? So you can solve this or you can solve for the decimal place of this, or decimal form of this, which is actually 1.732. So the radius at this particular depth for the circle, okay, of the liquid surface is 1.732. Of course, smaller than 2 inches. Okay. When we have our radius, we can now solve for the area of the base, which is now 3 pi square inches. So using the formula pi r squared, correct? Because this is in fact still a circle. So with our radius, or with the area of the base of the circle, with the area of the base of the cone, which is a circle, as 3 pi square inches and its height of 3 inches, we can now solve again for a volume, this time only at 3 inches of liquid depth. Okay, so 1/3 times 3 pi square inches times 3, okay, gives you now 3 pi square inch, which is now 9.4248 cubic inches. Of course, that's now a lesser volume than the capacity, and than the capacity of the glass full. Okay, so that's how you solve now this type of problems. Now there are of course, there are many other problems, a lot of problems out there for solid mensuration, okay, that will use the various formulas that I've given out a while ago, or are in this video, or in this particular module. So I suggest you try to solve problems regarding those, okay, different types of solids. Anyways, so as you notice, the problems here in solid mensuration are heavily reliant on the formula. So if you know the formula, then you can already, you can solve problems quite easily. Okay, so if you try this one, so in your own, okay, so in the corner of a cellar is a pyramidal heap of coal. The base of the heap is an isosceles right triangle whose hypotenuse is 20 feet, and the altitude of the heap is 7 feet. If there are 35 cubic feet in a ton of coal, how many tons are there in this heap? So again, this problem is a bit hard to solve if you do not draw it first. So you try to draw this first. Imagine the scenario, okay, so in a corner, of a wall, okay, so if you stack coals there, they form, according to this problem, pyramidal heap of coal. Okay, so ideally, so try to solve this one for my class. So you're not required to submit this one, so for my class, but for Engineer Angloan's class, so you ask him, okay, if he would like you to submit this one. So this one, okay, and that is it for solid mensuration, and I guess that's also it for bridging mathematics. So it's been a pleasure discussing this subject with you, and I hope for the majority of you, we see you on differential calculus on the next term. Okay, questions, send them in our inbox in Canvas, and I'll see you. Oh, I guess I will not see you on the next one. I'll just thank you.